This short lecture is intended to introduce you to the concept of facies. So what is a facies? A facies is the sum of all of the characteristics of a rock unit. A facies can be descriptive. For example, cross-bedded sandstone facies. When I say those words, a picture emerges in your mind of a sandstone that has crossbeds in it. So it's a way for us to talk about a set of rocks with a common understanding. A facies can also be interpretive. For example, a fluvial facies. And in the coming lectures, we're going to talk about different depositional environments like fluvial systems, which are river systems, and you will learn the descriptive facies that fit within interpretive facies. So you will learn the descriptive facies, things like cross-bedded sandstones, and what interpretive facies, like fluvial facies or beach facies or deep ocean facies, you might find those in. We define facies from the depositional environmental processes that generate a sedimentary facies response. So certain depositional environmental processes make cross-bedded sandstones. Other depositional environmental processes make laminated muds. So those sedimentary facies are responding to the conditions of that environment. So we've been starting to learn about some of those environmental conditions, so now we can fit those into particular places on the globe where deposition is happening. I should mention here that not every single depositional environment has a unique facies. They share certain descriptive facies with other environments. So where can a cross-bedded sandstone be found? We can find a cross-bedded sandstone at the beach, depositional environment number 6, in rivers, as we just mentioned, the fluvial facies, in delta environments, number 5 here, in tidal channels, like number 7, and in wind-deposited dunes in the desert. So we need to learn a little bit about these different environments of deposition to know what sort of descriptive facies fit within each one. In general, any environment that tends to be above sea level primarily undergoes erosion. We have this idea that mountain ranges and any rock that's exposed above sea level is exposed to physical and chemical weathering and is being eroded. But there are areas of deposition above sea level, in glaciers, in desert lakes and deserts, rivers and lakes. These are all places where deposition is happening. However, the primary thing that's happening in the terrestrial realm on land is erosion. This is in contrast with below sea level, where primarily we have deposition. So our beach sediments, continental shelves, reefs, the continental margin and the slope in the deep sea, full of turbidity currents, this is where we primarily have deposition happening. So what we use is an actualistic facies model. If we are going to interpret the different depositional environments, we need to have an understanding of what happens today, the present, and use that to refer back to what probably was happening in the past. Another word for this that you might be familiar with is uniformitarianism. Uniform, the idea that these processes have stayed the same throughout geologic time. That the way glaciers that you see in the top right, braided rivers that you see in the bottom left, the way those systems operate today is the way they were operating back in the Cretaceous, back in the Cambrian, and back in the Precambrian. So when we make actualistic facies models, we are making observations of modern depositional environments and inferring the structures and sediments that we see in the present and using those to interpret the past from the rock record. One way that we understand how different rocks and sediments relate to one another is Walther's law. Walther's law is a rationale that we can use to interpret vertical facies successions. What does that mean? That means if you're at the beach and looking at an outcrop, or or if you're looking at a core, the way the rocks stack up on top of one another, that's the vertical facies succession. You're seeing different rock types, and how are they related to one another? The idea behind Walther's law is that these vertical stacks of rock represent the migration of laterally adjacent depositional environments. So the idea here is that sea level might rise and fall and cause each of these depositional environments to move further on land or further out to sea. So the vertical set of rocks that we get might represent how environments have changed through time. So we can make interpretations of what environments we have been in the past based on this vertical stacking of rocks and the depositional facies that we see in each of these rock units. So we're going to take a quick break to watch a short video on this topic with a little bit of animation that I hope will make this concept a little more clear.
Okay, to explore Walther's ideas about patterns of sedimentary facies, I want us to think about a landscape from two different perspectives. The upper perspective here shows a map view, sort of like a Google Earth view, if you will, of different sedimentary settings, where the sediments are spawned in a mountain range over on the left, to being transported downstream in a braided river system, and then going into a more mature trunk-like river that then meets the ocean in a little delta, spreads sediments out along a beach, and then the shallow ocean water, the flooded part of the continents, the continental shelf, and then the deeper ocean further offshore. If we translate that into a drawing here, it might look something like this, and then we can take that and add some locations to it. And we'll just call these A, B, C, D, and E for simplicity. Now let's transfer that information down to the block diagram that we see down here at the bottom. So for right now, we'll cover the sides because we don't have any information yet about sediments' long-term pattern of accrual. And let's put the sedimentary settings on top of that surface. And you can see sea level over there. On the right, where the sea meets the land, is the shoreline there, and that's at location C, roughly. And then we've got A and B in the terrestrial realm, and then we've got D and E in the marine realm. Now we want to think about the sediments that accumulate in these different settings. So let's go ahead and put different sedimentary facies down here. So we've got kind of a gravel facies at the most upstream end of the system, then coarse sand at B, finer sand at C, and then offshore we've got silt for D, and then clay at location E, furthest offshore. Okay, so if we give a little bit of time to the system and we keep sea level in exactly the same place, maybe we build up something like this. So deposits of gravel at location A, deposits of coarse sand at location B, deposits of fine sand at location C, silt at D, and clay at E. Now what happens if sea level goes up? Well, sea level goes up and then all those different facies track with the new sea level going inland. And if sea level were to go up a little bit further, they would track inland a little bit more. Now we see a pattern down here in the wall that's facing us where we have coarse sediment that we started off with that's overlain by finer sediment. So in other words, more nearshore facies are overlain by the deposits from more offshore locations. If we had a series of cores that were drilled down at locations A, B, C, D, and E, we might get something like this. So location A shows the original gravel overlain by coarse sand, overlain by fine sand. Location B doesn't show the gravel. It just shows coarse sand overlain by fine sand, overlain by silt. Location C, fine sand, silt, and then clay. And then locations D and E, you can see they're basically clay dominated. D's got a little bit of its original silt deposits at the bottom, but then as sea level went up, that location got to be deep and offshore and basically only accumulated clay from then on. And location E has been offshore this whole time. It's been really far away from the original source of clastic sediments, and so we've got nothing but clay to show for it.
You were able to see how as sea level was rising, all of these depositional environments were moving toward the land. And we end up with these stacks of vertical associations of rock that allow us to make interpretations of how the depositional environments were changing through time in the past. Again, remember your principle of superposition, the idea that in general, the rocks at the bottom of your stratigraphic section or your core were deposited first, followed by the next package, followed by the top package, which is going to be geologically youngest. We've been looking at sedimentary structures as a way to help make sure that our packages of rock have maintained that superposition integrity throughout tectonic changes that may have occurred to those rocks. So what is a facies model? What we're sort of getting at here is the collection of rocks, the lithology, so the type of sediments, the type of structures, the stratigraphic association, so this is what we've been talking about, how the beds are stacked up on top of one another, which rocks are related to others, which are associated with others in the stratigraphic column, which rocks are touching one another and changing through time. And then the 3D geometry. So how are these rock units continuous along the outcrop or across broad spaces like entire states or parts of the continent? So we can use the lithology, the stratigraphic association, and the 3D geometry that would be expected from the migration of depositional environments within a particular depositional environmental setting. So again, we are using what we know about the present, what we know about how a sandy braided river might migrate, might move within its depositional setting, how a wave-dominated delta might move within its depositional setting. We are using what we know about current depositional environments to then infer what is the collection of rocks, the stratigraphic association, and the 3D geometry that we would expect to see if we were looking at the rock record. So here is the kind of facies model that one might draw up for a set of rocks. So on the left-hand side is a picture of an outcrop and the corresponding model that's been drawn on the right-hand side. So a geologist has made some interpretation of the types of rocks that they've observed, like framework-supported conglomerate, siltstone, sandstone, peat, pebble-rich mud, planar laminated siltstone and fine sandstone, cross-bedded sandstone, and framework-supported conglomerate. You are familiar with some of these rock types, and some of these rock types you might hear their names or see a diagrammatic representation of them, and it might conjure for you a particular amount of energy, right? Because that's what we've really been focused on so far. Conglomerate, for example, is going to take more energy to erode and transport and deposit these larger clasts than laminated siltstones and fine sandstones, right? So you are already getting the sense that the depositional energy was changing as you go from the bottom of this column to the top of this column. Now we can start to use some of the structures and how these rocks are related or stacked on top of one another to infer what kind of environment might this have been. So we won't be doing this yet today, but we're going to start to move through all of these different depositional environments in our lectures. So here's a handy checklist that can help you when you are in the field and when you're in the class in the lab to make sure that you're really getting a handle on what has to go into understanding a facies. So you need to know the main sediment type or types. Is it silt? Is it sand? Is it gravel? Etc. You need to know the common sedimentary structures, both primary and secondary structures that we've been talking about. And then you need to look at a bed-to-bed comparison. Are the beds, as they stack on top of one another, getting more fine? So are you going from conglomerate to sand to silt? Or are they coarsening as you go upwards? Are you going from silt to sand to conglomerates? And are there any unconformities? Do you see any contacts between the beds that are irregular, or a sudden jump or change in the type of sediment that you see? And then you need to tell, are the beds laterally continuous or discontinuous? As you walk along the outcrop to the left or right-hand side, do some of the beds appear and disappear, or do they extend for many meters? Do they extend for many kilometers? Do they extend up and down a a shelf or up and down a state boundary, for example. So all of these pieces of information are going to help us reconstruct different facies. So now that you have this basic information, you're ready to start to learn about all the different depositional environments that we have on Earth today and get a feeling for what they look like in the rock record.